Okay, we're in chapter 3 on determining change derivatives. Now this is section 3.1 on simple rate of change formulas. So we've been looking at rates of change and we've done it graphically, numerically, and algebraically. And now what we're going to do is we're going to look at derivative formulas for power functions and related functions formed by addition, subtraction, and multiplication by a constant. And they're going to be all presented in this section. And after that, we'll be able to use those formulas to actually do our derivatives instead of either the graphically, numerically, or algebraically. So the first one we're going to look at is rates of change of constant functions. So what is a constant function? It's just a function with f of x equals some number or some constant, okay? And it's represented graphically as a horizontal line. And so what is there? There's no change taking place. So the slope of the horizontal line and the rate of change of the constant function are 0. So in kind of rule format, constant function, the constant rule for derivatives is we just have if f of x is equal to b, then f prime of x is equal to 0. So, if we had f of x was equal to, say, 5, then f prime of x is equal to 0. It doesn't matter what our constant is, the derivative is always going to be 0. What about rates of change for power functions? Well, if you remember, power functions are a function in the form f of x equals x to the n, where x is our input variable, hence the x, and n is some non-zero real number. So we're raising it to a power. It could be a positive, it could be a negative, it could be several things. So, whatever it is. And it's possible to prove using our limit definition of derivative that the rate of change function for the power function is basically if you have f of x equals x to the n, then the derivative of that is n times x to the n minus 1. And now this is simply known as the simple power rule for derivatives, and it gives us our power rule here. So f of x is equal to x to the n. And then we just say, well, f prime of x is equal to n times x to the n minus 1. And if you notice, what we've done is we've taken what's up here, our n, brought it down in front here like this, and then we subtracted 1 from our numerator or from our exponent. So then it becomes n times x to the n minus 1. Okay, and n is any non-zero real number again. Okay, so that's the key. We take our exponent. So if we had x to the fourth, and that was our f of x, then f prime of x is going to be, now we're going to bring the 4 down in front, and then it's going to be x, and we take 4 minus 1, so that's a 3. Okay, so that's how that's going to work. We just bring our exponent down and then subtract 1. And I'm sure you've noticed that as we've done derivatives using, the point and close point or the limit rule or whatever, that's how we end up with the values. All right, so now looking at this, the figure below shows a graph of a function f along the graph of a function that is constant multiple of f. So we have our normal f, which is the blue line, and then what we've done is we've taken 3 times f, and that's our dotted line. Okay, so if we took, just certain points along the way, in this case we had this one, we take it times 3, we're just taking our f part times 3, our y, the f of x part, and so 3 times that's going to give us 4.2. And then this one we had a negative 4.3 times 3, negative 12.9. Here we had, 5, that gives us 15. And so, we get the new function, that's the dotted line. So we basically are amplifying the output of a function by a factor of 3. This is another way, if we have this one, what we can see is 3 times f prime. Well, this is our f prime, so we've already taken the derivative, and 3 times it, well, basically we're just taking that times 3, and we've moved that down here. And if we have these 2 points, they're going to be 3 times that, and so it's going to kind of push it down and shrink it up. So it's going to, push it in like this, and it's going to push that down like that. And so it's going to affect the behavior of the function when we get done. Okay. We have also linear functions. So say we had k, and if we multiplied that by 0.8, that would be our line. Then if we multiplied k times 0.5, we would get that line. Well, what does that give us when we take the derivative? Well, the derivative of k is just going to give us 1 because that's just a constant, so it's 1. Now the derivative of this constant, well, that's going to be zero point 0.8 times 1, so that's that. And if we take the derivative of this, if we pull that out front, that's 0.5 times the 1, and we get 0.5. And so we're having an effect on that. It's a constant multiplier, basically, and it just we're pulling it out in front. And so then we're looking at 0.8 times the derivative of k, and 0.5 times the derivative of k, okay? And what if we take and multiply by a -1? Okay, well, here's our original function. We multiply by a -1. What it does is it flips it over the axis here. And so that gives us, this kind of mirror image over the x-axis. And so, if we take and find the slope function of that and go that way, that gives us this function. And that's going to be, our point of inflection. So that's going to be that peak here. And same thing here, that's going to be the point of inflection. So that's going to be our trough in this case, our lowest point here. And so it works kind of the same way, because if you think about this, if we reflect it over, we're down here. And so it's basically a reflection as well. So what that means is, with the rate of change function for functions with some constant multiplier, 3, 4, -1, whatever, the effect of a constant multiplier on the rate of change of a function, we illustrated that with the previous figures there. And so we can use the limit of definition of derivatives, and it can be shown that the constant multiplier basically acts on the rate of change function exactly as it does on the original function. Okay, so if we had, say, f of x equals c times g of x, where c is some constant, then what we can do is when we take the derivative of f of x, we get f prime of x, then we're just going to have c times the derivative of g prime of x. So we just pull out that thing. So maybe we had f of x equals, I don't know, 3x squared. Well, then if we take f prime of x, that's going to be 3 times the derivative of x squared. So it's going to be 2 to the x to the 1. And so it gives us 6x. And so, we've done basically multiplying it times 3. So we've pulled it out front because it's going to be easier, because then we can just work with the x squared. And we know when we take the derivative of x squared, that's 2x. And then that's just taken times 3. So we get our 6x. Okay. Now this one's a little more complex. Here what we're doing is we have a function f, and we're going to add to that the function g. So if we look, we have certain points picked out here. So we have 0, 8.4, and then we have 0, 0.12. So we're going to add those two together. Well, 0 plus 0 is 0, and 8.4 plus 12, well, it gives us 20.4. And then we do the same thing here. 2.5, 12.6, 2.5, 8. Well, it's going to be, then gives us, goes up to the 2.5 and then 20.6. And then they also put an extra point in here. It's kind of the in-between one, but we're not going to worry about that. We're really looking at the ones where we have the same values, okay? And so then we have 7.4 plus 4 gives us 11.4, and so on. And so basically, f plus g gives us the f plus g there. So that's kind of a nice thing with that one. Now, does that give us the same thing when we take derivatives? Well, if we have f and we take the slope graph of it, we're going to get something like this. Looks like it's probably a cubic, and so when we get done, we should get a quadratic, and that's kind of what we have here. And it gives us points along the way, so we could do that with the slope graph. Same thing here. This is our original, then we take the slope graph, and we know that's going to be a 0, that's going to be 0, and that's going to be 0. So those are our 3 zeros. That's going to be a minimum, that's going to be a maximum. We get those. That looks good. And now if we add this to this, is that going to give us that? Well, if you look, 0 and 4.8 and 0, 0, it's going to be 0, 4.8. That looks good. Okay. Now we have 5, 2.7 negative, and 5, 0, so it's going to be 5, negative 2.7. Now we have the 2.5 and 2.5 and negative 0.8, negative 2.5. That gives us a negative 3.3. And as we go, that plus that does equal f prime plus g. Now, does that equal the slope graph of this? Well, we're going to have a slope of 0 here at 1. Well, that's going to be about 1, I'm assuming. We're going to have a slope here about maybe 6 or 7, and that's going to be about the same as here. Okay, that looks okay. And so here we're going to have some kind of a decrease, and it's going to switch. So it's going to be about here is going to be a minimum. And if we kind of go down here, that's going to be our minimum here. And then we're going back up. So it does match as far as when we add those two functions together, we get this function. When we add this function plus this function, the derivative functions, we do get f prime plus g prime, and that is the slope graph. Okay, so it does work out that way. And so what we can say then is the rate of change functions for both sums and differences. We only showed the sums, but it works also for differences. So if we have h of x is equal to the f plus g of x, then h prime is going to be f prime of x plus g prime of x. And same thing for difference, except now we have subtraction. So that's going to help us when we have functions where we have, the f plus g of x, then we can take and do the separate f prime and g prime. Now, rate of change for polynomial functions. So basically what we can do is we can take all the rules we just learned and put them together, and we can look at it for polynomials. And so we could have something like maybe, f of x equals 2x squared plus 4x minus 1, okay? And we want to find what is f prime of x. Well, we're just going to work piece by piece and take the derivatives at each point. So that's going to give us 4x. That's going to give us plus 4, and a constant that's going to give us 0. So we can put plus 0, or we say we're done at that point. We don't have anything when we take the derivative of that one. So we could have taken each piece and looked at the derivative of each piece, or we just go across and we know that when we do the sums or differences, then we just have the sums or differences in our derivative as well. Okay. So that's a nice thing about all of these. Now we can directly see, hey, this is the derivative of this, and we didn't have to do that point and close point and do all the algebra. And we also didn't have to do the tables, if we wanted to say, what is it? The x approaches, 7 from the left, and then x approaches 7 from the right, and then do those limit tables. We didn't have to do that to find that. We just used our formulas and we got our derivative directly. Okay, so that's going to be a nice thing we can do now. All right, I'll stop there and then I'll start doing examples.